In this chapter, we examine the nature of friction. You will notice that this chapter is subtitled Introduction to Tribology. Tribology is defined as an area of study that focuses on the design, friction, wear, and lubrication of interacting surfaces in relative motion. Our focus, though, is going to be restricted to dry friction. Lubricated surfaces interfacing metal to metal in relative motion is a complicated fluid structure interaction that some of you will study further in mechanical engineering. We will begin by discussing the observed nature of dry friction. Our approach might be called phenomenological. That is, our description of the nature of friction will be inferred from observation, as opposed to a first principles treatment based on the atomic interaction of adjacent surfaces. There are engineering faculty members whose research area includes the study of friction on an atomic scale, so there are people trying to formulate a more fundamental description of friction, but our treatment will be more macroscopic. We will begin by looking at an individual particle problem where there is only one frictional contact surface. We will then examine a problem involving a body on the threshold of motion. Body problems are complicated by the fact that there are two general kinds of motion for a body, translation and rotation. Impending motion may be sliding, translation, or tipping, rotation. It will often not be clear which type of motion is likely to occur first, and we will have to examine both possibilities to reach a conclusion about the nature of the impending motion. We will then transition to problems involving multiple frictional surfaces. The latter problems are more complicated in that there is no guarantee that two surfaces that might slip will do so simultaneously. Most of the time, slip occurs at one surface before the other. You can think of these problems as variations of limit load problems, where not every structural element fails at the same threshold exerted on a structure. Not every frictional surface slips at the same time. We will close Chapter 9 by looking at one application of friction, that dealing with belt friction. Here we'll relax our assumption that pulleys are frictionless and examine the torque that can be transmitted by a pulley when it is designed to grab a belt through frictional contact. There is a simple experiment we can conduct with almost any object resting on a flat surface using a scale. If we have an object at rest on a table and hook the scale to it and start pulling, we observe that initially the reading on the scale increases as we pull harder, but without any displacement of the object. If we plot force versus displacement, we climb the curve vertically until we reach a critical point where the object suddenly slips. It is typical to find that the force required to continue the motion is smaller than the threshold force required to initiate the motion. So if we keep pulling so as to drag the object across the surface, we would typically find that the force registered on the scale decreases slightly once the motion begins. We can get a crude idea of why this is the case by imagining the interface between two interacting surfaces. At the microscopic level, these surfaces really aren't flat. If we blow this up, the interacting surfaces will look something like this. They have an irregular distribution of dimpled features we call asperities. At the microscopic level, these look like interlocking mountain ranges when the surfaces come in contact. When we first start pulling on the body, the initial force is insufficient to overcome the interlocking, but eventually we reach a threshold level where the asperities start moving past each other. Once they start moving, they don't interlock with the same tightness as when they were stationary, and the force required to get them to continue to surf over one another is less than the force required to overcome the initial interlocking. Note also from the free body diagram that the frictional force exerted on the object at the surface acts against the direction of motion. This is an important feature of friction. It is always a dissipative force. If we drag the object across the surface, then turn around and drag it back to its original location, we will not recover any of the effort required for the initial displacement. In this regard, friction differs from other forces we've discussed. In particular, I've been telling you all semester that when we have a free body diagram, we just need to represent the presence of the force with some direction, then let the algebra tell us whether we guessed its direction correctly. Friction is different in this regard. Friction must always be represented as opposing the direction of actual or impending motion because it is always a source of dissipation or loss. Based on observation, the threshold force required to induce slip is found to be proportional to the normal force between two bodies. If you like, you can think of increased normal force as increasing the tightness of the interlocking asperities, making it increasingly difficult for one set of asperities to slide past the other. The constant of proportionality, mu, is called the coefficient of friction, and all the interesting physics behind interacting surfaces is buried in mu. Consistent with the visual of interlocking asperities, the friction coefficient depends on the type of interacting materials, the surface roughness, that is, the microscopic height of the asperities, environmental and other factors. It does not depend on contact area or, in the case of sustained slip, the sliding velocity. Because there are often two different kinds of friction, impending versus sustained slip, we sometimes use two different friction coefficients to relate the friction force to the normal force. In the case of the threshold force to initiate motion, we use the friction coefficient mu sub s, called the coefficient of static friction. In the case of sustained motion, we use the friction coefficient mu sub k, called the coefficient of kinetic friction. This table provides representative values for coefficients of kinetic friction between different interacting materials. A couple of important points can be made from this. First, the crude nature of our description of friction means there is no point in quoting a friction coefficient out to 3 or 4 significant figures. The best we can do is provide a range based on the factors influencing the interaction. Second, friction coefficients are not restricted to values less than 1. Illustrations are often given using values of mu sub s or mu sub k in the range of 0.2 to 0.3, but some material combinations, steel-to-steel surfaces for instance, can result in values exceeding 1. The observed behavior of dry friction can be summarized in Coulomb's law. Before slip occurs, the friction force can have any value between 0 and the threshold required to initiate slip. After motion begins, the friction force is the product of the normal force and the coefficient of kinetic friction. This also highlights one area where novice problem solvers often make mistakes. Asked to describe the nature of friction, many students will respond that it is the product of the friction coefficient and the normal force. But this is only the case when there is impending or actual slip. If slip is not imminent, the friction force can have any value between 0 and the threshold for slip. This distinction becomes important when we are trying to determine if threshold motion involves sliding, where a body is on the verge of sliding, or tipping, where a body is rotating about a contact point where slip is not occurring. Unlike our previous problems, where we represented a force and let the algebra tell us whether or not we correctly guessed its direction, we must represent friction as opposing actual or impending motion. Sometimes, as in the case of a body undergoing pure translation, this is straightforward, but in many instances it is more complicated than that. Consider, for instance, any vehicle with wheels. Most of the time, we can't consider the wheels and vehicle together as a single rigid body, as the wheels are obviously intended to rotate relative to the body. What direction does friction act on the wheels when, literally, the rubber hits the road? Consider these two different cases. On the left, an airplane is coming in for a landing and deploys its landing gear. There usually isn't any mechanism for spinning up the wheels to be consistent with the plane's landing speed, so until the plane touches down, the wheels are in a state of pure translation and moving with the plane's speed. Until the plane touches down, wheels and aircraft can be treated as one rigid body. At the moment of touchdown, the velocity of a wheel's material point adjacent to the runway is in the same direction as the aircraft, and the friction force exerted by the runway on the wheel is opposite to the plane's direction. This serves to both provide a modest braking force, slowing the aircraft, and also to exert a frictional torque that spins up the plane's wheels until they stop sliding. Look at any airport runway and you'll see skid marks at the end of the runway. The length of those skid marks tells you how long it took for friction to spin up the airplane's wheels until they stopped sliding. As a second example, consider a dragster sitting at its starting position on a racetrack. A typical dragster is a cartoonish vehicle with an absurdly large engine, long narrow body, and hugely fat rear tires. Before the light turns green, the dragster is stationary, so neither it nor its wheels experience any translation. As the light turns green, the driver pops the clutch and a ridiculously large torque is applied to those rear wheels. For an instant, the wheels are experiencing pure rotation. Now a material point on the tire adjacent to the track is trying to move backward under this torque, so the friction force acting on the tire is forward, towards the vehicle's front. This is in fact how the vehicle gains traction, and this pushing off the track is what enables the vehicle to gain linear acceleration down the track. Eventually, as the linear speed of the vehicle increases, the slip between tires and track also diminishes. The point of these illustrations is that friction can act in one direction or another, depending on the local relative velocity at the point of contact. I chose two extreme illustrations where a body began with pure translation, that is, the plane coming in for a landing, or pure rotation, the dragster tire's initial motion. But most of the time there are competing effects that make it difficult to tell definitively what the nature of the relative motion actually is. For this reason, we often have to revisit the problem after we've solved to make sure our initial assumptions are self-consistent. We'll take a look at examples of this momentarily. To start, we consider this relatively simple example involving a block on an incline. The block has the advantage of being treatable as a particle, so we don't have to worry about relative motion of different parts of the block. We want to determine the range of values for the force P, for which the block will not slide, given that the coefficient of friction is 0.2. You might also notice that there isn't a subscript on this friction coefficient. If there isn't a subscript, this often indicates that there is no difference or little difference between the static and kinetic friction coefficients, and we'll just treat them as one and the same. To answer our question, we consider two different free body diagrams, depending on whether we're considering imminent motion up the incline on the left or down the incline on the right. We are interested in the threshold for slip, so the friction force is set equal to its maximum value of mu times n. We have two different cases, with friction opposing the impending motion in both cases. Looking at a normal tangent coordinate system, where the tangent direction is along the incline, we see that the equilibrium equation in the normal direction is unchanged between the two cases, giving us a normal force of 60 pounds. The tangent equation does differ because of the changed direction of the friction force, and this ends up giving us P equals 80 plus or minus mu times n pounds. The result is that the block remains stationary as long as P falls into a range between 68 and 92 pounds. Sometimes an angle of friction is used to describe the range of orientations of a supporting reaction force on a frictional surface. Because the friction can be as large as mu times n, the tangent of the angle made by the reaction force with the normal force can be as large as mu. Note this also provides another way of justifying a purely normal reaction force on a frictionless surface. If there's no friction, mu goes to zero, and the locus of acceptable reaction forces shrinks from a conical shape to a single vertical line normal to the surface. Consider now a second example involving the largest force P we can apply to a tub of ice cream before we cause it to move. This may look similar to example 1, except that you'll notice we didn't have any dimensions on the block of example 1, and we do now show dimensions of this tub of ice cream. This is an indication that we are to treat the tub of ice cream as a body and not just a particle, So we will have to consider two possible types of impending motion: sliding, translation, and tipping, rotation. It isn't obvious by inspection which motion is more likely, so we'll examine two different cases and look for a self-consistent solution. Consider first the case where imminent motion involves sliding. When no force P is applied at the upper right, the ice cream is uniformly supported, and the effective center of the concentrated normal force is right in the middle of the tub. The lines of action of the weight of the ice cream and the normal force are coincident, and the ice cream is in equilibrium, just like this. As we begin to apply a force P to the upper right, the distribution of support changes. The tub tends to lift off the surface right underneath P and develop more support on the far side of the tub. So now the distribution of normal force under these conditions might look something like this. This asymmetric distribution of support means that the effective center of the normal force shifts to the left. We don't know where this effective center is, though, and it becomes one of the unknowns in the problem. I'm going to refer to this distance in our future solutions as x. It will be the location of the normal force measured from the geometric center of the tub. This leads to the free body diagram shown here. Because the premise is that sliding is imminent, the friction force is set to the product of the static friction coefficient and the normal force. The unknowns are the force P, the normal force N, and the effective center of the normal force labeled x. Because x represents the effective center of the normal force, it must fall somewhere between 0 and half the base of the tub. So our consistency check asks, does x fall into an acceptable range? And in particular here we must find that x is less than half the width or half the base of the tub. If we instead consider the case where tipping is imminent, we have a different free body diagram. Now the premise is that the tub has lifted off the surface but sticks at the lower left end. The entire normal force is now supported underneath this left edge. So we know where the normal force acts. The friction force has not yet reached a level where sliding is imminent, so we can only represent it as F. The problem unknowns are forces P, N, and F. The consistency check now takes a different form. We need to ensure that F is not too large relative to N, so we will verify that the ratio of the friction force to the normal force is less than or equal to the static friction coefficient. Now let's take a look at the complete solution. Here I've reproduced the two free body diagrams just discussed, along with the consistency checks we'll use to examine the self-consistency of the solution. For both of these, I'm going to use force equilibrium in x and y and moment equilibrium about the center of gravity to solve the problem. Summing forces in x, we have simply that for the sliding case, we have Sn minus p is equal to 0. Summing forces in y, we have n minus w equals 0, or just n is equal to the weight. And summing moments about g, we have force P times half the height minus the normal force times x plus the slipping friction force times h over 2 is equal to 0. Using the moment equation to solve for x, we have that x is equal to the ratio of p over n times h over 2 plus mu s times h over 2. But from our force equilibrium equation in x, we have that p is equal to mu s times n. So the first term also becomes mu s times h over 2, and the result is that x is equal to mu s times h. Using the value of 0.6 for the static friction coefficient, we have that x is equal to 0.6 times the height of 8 inches equals 4.8 inches. But the base of the tub is 7 inches. Half of that is 3.5 inches. We ask, is this less than 3.5 inches? And the answer is no. So this is not a self-consistent solution. For the case of tipping, if I employ the similar equations, I'm going to have in x, f minus p equals 0, or f is equal to p. In y, n minus w equals 0, or n is equal to w. And if I take moments about g again, I get p times h over 2 minus n times b over 2 plus f times h over 2 is equal to 0. From this last equation, and using the fact that f is equal to p, I have P is equal to F is equal to the normal force times B over 2H. The check then becomes to see that F over N is B over 2H, and with B equal to 7 inches and H equal to 8 inches, this is 7/16, and that value is equal to 0.4375. That is less than 0.6, which is the static friction coefficient. So in fact, that is a self-consistent solution. And our force P required for initiating motion, which is tipping, is N is equal to W. So this is W times B over 2H. So it's 0.4375 times 9 pounds, and that's equal to 3.94 pounds.